We're going to solve an exercise in Python Jupyter notebook that is here on the screen. So essentially, the exercise is saying that you have been invited to the Gunnerus ship, a vessel that belongs to NTNU, and you're going to do some activities, research activities in the Norwegian Sea. Okay, the vessel will be on the area where Ostahanstein will be placed, or is already in operation. So Equinor is sponsoring your stay and your trip on the ship. Okay? The ship is equipped with a buoy that measures the wave elevation every 0.5 seconds. So just to show your gratitude to Equinor, you're going to take the wave elevation data that is processed, okay, that was gathered for a period of almost an hour during the trip, and you're going to apply the FFT, the fast Fourier transform, and then you're going to make a plot to determine the spectral peak period of that signal. Okay, so we're going to do that in in a Jupyter notebook. And in previous years, we have done it using Excel, but really Excel has some limitations. Excel can do FFT, but has some limitations um, where the number of data points have to be up in the power of 2. So it can be 2 to the 4, 2 to the 5, 2 to the 6. It cannot be any other number. So in a more flexible way, Python will use Python, which is more flexible to take any number of data points we have. And also FFT is a nice tool to learn because you can use it for many other transient phenomena. Okay? Like I told you before, if you have some excitation, can either be a force, can be variation of pressure, can be variation of rate, and it seems very random, its variation. You can apply an FFT and see the spectra. And if the spectra shows that you have some range of frequencies, some range of periods which are the most significant, which are the most relevant, that tells you that you can represent a big part of the wave or the most of the energy of the wave with with that frequency. Okay, might be not only one, but might be a few, and also tells you something about how will that affect your system. Okay, if your system is susceptible to some particular range of frequencies, then it's important to do that. So we're going to solve this exercise using. So first, I also want to. I'm going to put the link here. There is a beautiful animation or lecture about how do you make this fast Fourier transform, the discrete Fourier transform in YouTube. Let's see if I can paste it here. And I'm sharing the link with you on the lecture, but if you have any questions about how this is done, I think this is a very nice video where it shows you step by step how you should do it. We're not going to go into details in this lecture, but simply I place the link here so you can click on it and you can watch it. Has a complementary material to the lecture. So we go to our CoCalc and we create a new project. We can call it wave analysis, wave data analysis. Okay, we have to create a project first. Okay, and we have a file that I took from an Excel file, the original Excel file, that depicts time in one column. Remember, data sample area every half a second, and then the elevation. Okay, the elevation over and above the sea level. So you have 0.8 sea level, and then you have minus 0.5 and so forth. And you have 2000 and something 4,000 and something data points. Okay, that's the thing, the limitation in Excel. You need to have a number which is 2 to the powers of something. Okay. So this file is something we're going to use. We have to load here. Okay, so we first load that file, and that file we call it data. Okay, and we are going to simply to load these files here. I think we can simply drag it. Sure if it's okay. It's already saved here below. And then the next thing we're going to make is we're going to create a new Jupyter notebook. Okay, and this we call it wave analysis. Okay, the same, almost the same name as the project. We're going to say it's where do we say it? Create. Okay, we're going to use Python 3. Okay, and it already started. But you see, in this project we have essentially two files. Okay, we have the Jupyter, and we have on the same folder we have this data file. Okay, I think if I close this one here, you will see, okay, the two files we have the Jupyter and we have the data file. So I need to load this file on Python to do my calculations. Okay, and that's very useful. In all the previous examples we made, we put data on the Jupyter network, it's Jupyter notebook itself, but here we're loading data from an external file. They have to be on the same folder, but okay, so we go to the first step. We're going to use for plotting, we want to make plots, right? We want to plot first the raw data to see how it looks like, and then we want to plot the spectrum we obtain. So for that, we say put a comment, importing needed libraries. Okay, remember to make a comment, you use the hashtag, and then I'm using import, the command import numpy has np. This I will use to load the data from the text file to Python, and I will use it also to calculate the FFT. Yeah, and then I'm going to use the other library, which is to plot, which is matplotlib.pyplot has plt, just like what we have done in previous lecture. Hope I didn't make any spelling mistake. We run it. Okay, we go to the next one, and next one is simply reading and plotting a wave elevation data, measured data. Okay, from your stay in the Gunerus. Okay, so we call it first. We're going to import the file. So we call mp is very simple. Just load txt. Okay, in NumPy we have a module called load txt, and then we simply put the name of this file, which was elevation versus time.txt. Okay, it was a txt file, and that command is going to give me an array, okay, a numpy array, which is like a matrix. So I'm going to call that elevation, simply elevation. Okay, so if we simply print elevation, I want to see how things are going so far. Okay, so we have simply one matrix in which the first column is the time, and then the second column is the elevation, the corresponding elevation. Okay, so then I'm going to split those because we are going to see we just need to apply FFT is to the elevation values. Okay, and then to calculate the frequency vector, we are going to use just the time vector. Okay, so I'm going to say to split, I say time. I will create a vector now called time from that matrix. Okay, and that matrix I'm going to take, remember the nomenclature 0, 0. So that means take all the rows, okay, but then just take just the first column. Okay, let's take that and explain a bit on. Okay, we mentioned that elevation was a matrix, okay, where we had A, B, C, D, E, F. Okay, so by saying these two dots, they mean all rows. Okay, that means you're going to take all of these rows, but then this one says take only column 0. Okay, which this is column 0 and this is column 1. Okay, so that means I have to take just these guys here, which is the time. And then to take the elevation, I'm going just to take, so this will be the time, and these guys here are going to be the elevation. So I do that time, and then let's call it elevation. We don't need the original matrix anymore. Okay, so we can simply substitute by just this vector, and it will be all rows, but simply the first column. Uh, the next step I want to see, it's maybe we don't need that at the moment, but let's make a plot just to see how the data looks like. So I have to call this module PLT, and I have to say, please add a plot where I plot the time and the elevation. And then to make it nice, I'm going to add PLT dot title, and then I say elevation versus time. And then to the plot, I also add a label to the y-axis, which will be elevation set in meters. I don't want to use the Greek letter zeta, so I use an plot dot. It should be PLT, right? Not plot, but PLT x label. And here I say this will be the time, and that's t, and then I use seconds. What I use for the axis is the name of the variable, the symbol of the variable, and the units of the variable. And after I have these two, I say PLT show, just to show the plot, and let's see what do we get. Okay, so it seems quite a regular signal. Okay, I think this example, this signal was generated artificially, but there is another example where the signal was actually measured. So I think I took the example where this signal is generated artificially. Okay, if you want to see, this is not very nice or not very understandable. So if you want to restrict, for example, you want to see just a particular window, then you say PLT xlim, you make a limit on the x-axis from 0 to, for example, 200 seconds. Okay. We rerun it, and then we are plotting just from the range from 0 to 200. And then you start to see a bit more the signal, the elevation going up and down. Okay, I want then to do what I didn't do before, but I say the number of points, okay, that I have, and this essentially is going to be either the elevation vector or the time vector, and I ask for the size. Okay, and then we can print also the number of points, because we are going to need this later for the FFT. Okay, we have 4,096 points. So now comes the part where I'm going to make the FFT. And from here, I'm going to use two commands that are in NumPy. So I say FFT, the magnitude, okay, which is simply this spectral energy, okay, or simply the amplitude that I have. It will be NumPy dot the absolute, okay. First, let's make NP has a module called FFT, and has another module called FFT, and that will be elevation. Okay, so I'm applying, let me just insert a cell below, just make some space such that it goes a bit up so you see it on the screen. But essentially we are applying FFT, the fast Fourier transform, not FFT. Okay, I'm making a mistake here. FFT on the elevation. But you will see this gives me actually a complex number. If you watch the video that I gave you, the link that I gave you, you see that this will give you a complex number. So what you need to do is you need to calculate the absolute of that, the absolute value of that complex number. And that we do by saying numpy again and absolute simply. Okay, the absolute, you know, the complex number is like if you plot it on the y-axis will be the imaginary component, and the x-axis will be the imaginary component. The x-axis will be the real component, and the y-axis will be the imaginary component. Then the magnitude is simply the total length of the vector. Okay, so that's exactly what this function is doing. And then to obtain, we don't want to have this power, uh, uh, spectral power, so then we have to multiply. This is also explained by this video if you need to know. Points, okay, multiply by 2 divided by the number of points. Okay, so there we get the y-axis in my frequency diagram. If we see on the lecture notes from last time, we see that we have a signal in time and we apply FFT, and then we obtain the spectral energy, but in this case we are obtaining right away the amplitude because we are multiplying by 2 dividing by the number of points, and then we need to obtain actually the corresponding frequencies for each one of these points. Okay, to obtain the frequencies, okay, let's see, just to show you what this is doing before we, okay, I'm going to repeat it here just to show you how it looks like. Print, let's put print. Okay, you see you have a complex number. Here is only real, no imaginary component, but all the rest they have their imaginary component. And if you remember your math lectures, you see that this can be plotted in a x and y, where x is the real component and y is the complex component. Okay, and what you want, you have a point in some of the quadrants, either here, 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 and you want to calculate the magnitude, which is simply the length of the vector. Okay, then we don't need this. I told you we have to say np dot absolute of this guy, and then we multiply by 2 and divide by the number of points. Okay, to get it into a real number, and then we simply normalize by 2 divided by the number of points so that we get amplitude. We say here amplitude, estimating amplitude. Okay, then comes we have to calculate the FFT of frequency, the frequency vector, and that we do another function called np.fft.fft, in this case frequency. Okay, that is also included in Python. And here we have to say how many points do we have. That's why the number of points also was important. And we have to say what sampling interval we have. Okay. In our case, we know it's 0.2 seconds, but instead of coding it right in 0.2 seconds, I'm going to read it from the time vector. I'm going to do that by saying, take the second element of this vector and subtract it from the first element of that vector. Okay, we know it's 0.5, so we can just have written there 0.5. but to make it consistent such that if we maybe you have data later that you measure every millisecond or you measure every hour, then you're able to, the code will still be valid. Okay, you don't have to change anything. Okay, so let's print this FFT frequency to see how it looks like. And we're going to see now a bit how in this case it outputs some negative values which we don't care. Okay, which we don't care. We just want the positive values of frequency. Okay, so we say create another plot, PLT, we have to say plot, and then we want to plot FFT frequency versus FFT magnitude. We say the plot, the title, what will that be? That will be amplitude versus frequency. We can call it maybe FFT, amplitude versus frequency. PLT.xLabel, and this will be frequency in hertz. And then PLT, not plot, PLT xLabel, this will be amplitude AI, and this will be in meters. And finally, I'm going to show the plot. Okay, so you see, you get this amplitude AI. Okay, that means my wave. This gives me the height or the value of the coefficient in front of each wave component. Okay, if we can go back to our notes. Okay, remember we have this gives you exactly that in the units that we have, which is wave elevation, and gives you that associated frequency value. Okay, so it tells you that for frequencies you have very low amplitude. For this range you have relatively high amplitude, and then from this point on you have no amplitude. Okay. Don't pay attention to the negative part. Okay, so let's say plot, then we say PLT, xlim, and we say from 0. Okay, then we just plot positive. We can maybe make it from 0 to 2. Xlim. Okay, I should make it, yeah, that's a mistake. I have to put it just before. I have to do it here before I click on show. Okay, and that looks much nicer. And that tells you, so the peak spectral period, okay, will be the inverse of this value, which is this is 0.1, this is 0.8, 1 over 0.8. Okay, that is 1 over 0.8. That is so the full, what you get here is because of the Nyquist value. It tells you that if you, here I have tried to calculate the FFT also for values that are equal to this. So the number of samples that I should use is they will start repeating itself. Okay, if I continue calculating the FFT for values which are I yeah, that's also explained on the video. So I'm not going to repeat it here, but essentially it's this Nyquist criteria that I cannot take. I simply have to discard. The spectra will simply be symmetric. Okay, if I calculate for all data points that I have, if I calculate the spectra, it will be symmetric. Okay, so therefore I only have to take care of half of only part of it. Okay, in this case of the positive. Some other FFT calculators, like the one in Excel, essentially repeats itself is a mirror. So after one you get also a flat area, and then you get again this peak. Okay, but it's simply a mirror of of the spectra, and that simply is because of this Nyquist criteria. And then you have to note your have to cut part of the spectra. Okay, so in this case we cut that part of the spectra by saying xlim plot it just from 0, please. I'm going to paste it here. Maybe not here, but after the code, I will leave some space to put the code. Okay, so this value here I have on my chart. This will be the peak spectral period, okay, or frequency. So we say it's 1 over 0.8, I think, because that is 0.1. Okay, so this will be like 0.8, and that is equal to, more or less equal to, okay, 1.25. Okay, 1.25 seconds, okay, or 0.8 hertz. Okay, so repeat this exercise by yourselves, and this allows you to analyze any data which has erratic pattern or has not a clear pattern, but it allows you to detect in that data if there are any dominant frequencies and flag it. Okay, simply the biggest on the peak. Bye bye.